So tensors are just bigger maps. So we've got we imagine at each point P, I haven't been sort of putting in the point because in flat space-time, all the different tangent spaces at the different points are really the same. I'll put it in now. So we have VP, because we want vector fields, right? So we need a different vector space at every point. And we have V star P, capital. I see in my notes I used capital T. I know why now, because it won't lead to the confusion with little v we had before. So we have these two things. We've already defined them. And so now we can consider a map. So a tensor of rank KL is a multilinear map. So it has to be linear on all its arguments. But now, just where the one form was a map from one copy of the tangent space to numbers, now we get a bunch of copies. So it's a map from V star P, if you like, tensor product, or just, yeah, I guess you can tensor product the space. And we need to do that with itself k times. So k times V star P, and then get a map from, we also have slots for sticking in vectors, L times, and it goes to the real numbers. So it's the natural generalization of what we did for the one form, except instead of sending in a single vector, you now get to send in a bunch of dual vectors and a bunch of vectors. So our machine is a lot bigger now. So it's got more slots, still only one output. So you can see it's got k slots for one forms. So let's imagine just a bigger one where you get to put in k one forms, and another one where you get to put in L vectors. That goes in there. It does its thing, and at the end of the day, it spits out some number. Okay? And so we call that number, so if the tensor is t, then this number is t acting on all those vectors. So v1 through, oops, that should be omega. So let's put the omegas first. Omega 1 through omega k, and v1 through vl. Okay, and that's all there is to it. So now I've defined a tensor. Now, why is this interesting? Well, lots of things in physics depend linearly on the direction you ask the question. One sec. So, we saw an example with the gradient during the question of how fast does a function change. That depends in some direction. That depends linearly on the direction. So gradient was a nice machine for answering that question. If you thought about fluid mechanics, you end up with a stress tensor, which asks questions like, how does the force in a given direction act on a fluid in a different direction? And so that has two little directions in it, but it depends linearly on those two different directions. And so it's naturally described as a tensor. Okay, so just lots of things in physics depend linearly on directions because directions are interesting and important. And whenever you linearize to make an approximation, things depend linearly. Okay? Let's continue with tensors. So last time we introduced the notion of a tensor as a multilinear map, linear separately on each argument, from k one forms and L vectors to a number, and that number is denoted t, the tensor acting on the k1 forms you put in, and the v vectors you put in, and the answer is t with a bracket acting on those vectors, like we had the same notation for 1 forms. So one thing I should point out right away is special cases we're familiar with. So a 0, 0 tensor, well, that's like a map from nothing to numbers, so it's a number, right? So 0, 0 tensor would be a number, but a 0, 0 tensor field, one tensor for each point in the space, is just a scalar. Okay? So scalar, something you've seen before, that's a 0, 0 tensor. Now, let's next do a 0, 1 tensor. So what's that? Well, that's a map from 0, 1 forms and 1 vector to real numbers. We talked about that last time. That's a dual vector, or a 1 form. And then 1, 0 tensor, I'm going to claim is a vector. And why is that? Well, it has to do with this funny business of the double dual as isomorphic to the original vector space, right? So the way we've defined tensors here, a 1, 0 tensor is a map from one dual vector to the real numbers, right? And so that map you can think of as, I'm just going to define v acting on omega, the vector acting on the 1 form, as, well, that's just the same thing as omega acting on the vector, which we already defined. Okay, so if you like, this equation makes the connection between a vector as a map on a 1 form and the vectors we already considered, which were defined in this context with the isomorphism to position in the space, and later will be defined in curved spaces more rigorously. So for example, well, not more rigorously, differently rigorously. So for example, I was watching the video, which I uploaded to YouTube, by the way, of class last time, and I was like constantly accidentally thinking of a vector as acting on a 1 form, even though I had only told you that 1 forms act on vectors. And that's because of this, right? This is sort of, one can act on the other. They're both defined linear maps. And if you remember, the coordinate component notation for this was omega mu v mu. Okay? And Vivian made a good point that for this kind of formula, you can regard the dual vector components as a row vector and the vector components as a column vector. And this here is then just the matrix multiplication between the row vector and the column vector. Wolfgang, did you have a question?
Yeah, so I'm in principle, this makes sense, but I'm trying to like develop on that, and I'm wondering if the interpretation I have is valid. Where as we're writing like a 0, 0 tensor, that's a scalar, and it felt backward to say a 0, 1 tensor is a dual vector. But is the idea
well, that's just literally how we defined a dual vector. It was a map from one vector to real numbers. And I defined a 0, 1 vector, a 0, 1 tensor as a map from 0 dual vectors and 1 vector to tensors. That's literally the same definition.
That logic, I'm wondering if it's like, if we have this tensor, what we need to act on with it to get a real number. So like if we start with, 1 vector, then we need a dual vector to get back to a real number. If we start with one form, we need a vector to get back to a real number.
Linearly, yeah. If you want to get back to a real number with linear dependence on what vector you put in. Yep.
Okay.
Yep, that's right. Yeah.
I'm wondering, we've been talking about how, these different things that we write is like the tensor acts on this many stuff. So does that define what the tensor is? Because it seems like almost it's like two separate objects that you're like, this acts on that. But that doesn't necessarily mean we know what like the tensor is.
Well, so you can ask, I can give you the tensor by like writing down some components, right? But physically, the point is many questions in physics do depend linearly on a bunch of vectors. So, like the stress tensor representing the, material in this table. or whatever, like, you know, there's shear forces, like, you know, if you lift the table, the whole thing goes up, and that's because, you know, so if I push my right hand up, it pulls my left hand up too, right? That's a shear. And the way you account for shear is, well, I'm interested in the force that this one feels from that direction, but I'm interested in the force from that direction that's going in this direction. So there's two directions involved, right? And the answer for the force per unit area that this fluid element feels from that direction going in this direction is the element of the stress tensor when you feed in those two vectors. The result of the stress tensor when you feed in the vector right and the vector up. And that depends linearly on what vectors you feed in. So very physically, describing the stress in a bar or whatever requires a linear map from vectors to numbers. I don't know if that helps. It's the same thing I said last time, but it's not an esoteric mathematical definition made up by mathematicians to torture you. Like, it's very physical. All right. Now, put off this basis thing since we had questions about tensor product last time. Let's go over that. Whoops, that's not good. So slow. Let's move the basis down. And let's talk about tensor product. So up here, I'm just using the symbol x with an O over it to denote exactly what I say. It's something where you provide k dual vectors and L vectors. It's the space of providing those vectors in a particular order. And but we do want a notion of a tensor product of tensors. And so the idea is if you have a tensor T, which has rank KL, and if you have another tensor S, which has rank Mn, then we're going to define the tensor product, T, tensor S, and that's going to have rank, just you add them together. That's supposed to be an M. Yikes. And that again, so it's very clear, rank M. N, so that's supposed to be a tensor of rank M plus K, N plus L. And what is that tensor? Well, the only structure we really have available are these maps, right? The tensor was defined as a map from vectors in one forms to numbers, and so we have to use that map. And so we do the only thing we could do, which is we say that if you take T tensor S and you feed in, K plus M vectors and L plus N duals, then what do you get? I'm running out of room. That has to be equal to just T acting on, the first K vectors. Oh, wait, I'm sorry, I have this reversed. K is the number of duals, right? Yeah. If you guys notice that, you can shout it out, because the people who don't notice it will be very confused. So, right, you plug in K dual vectors in the definition. Okay, so I reverse that. So you plug in the first K duals, and then you plug in the first L vectors, and then you just multiply it by ordinary multiplication. The other tensor, which has slots for M dual vectors and N vectors, and then it's just the remaining, the rest, oh my gosh, the rest of the dual vectors and the rest of the vectors. Okay, so it's really the only thing you could do that looks like multiplication that gives you a tensor of rank t, of rank sum of the rank of the previous ones. Like they're numbers, right? So it's just times, right? Because t is a map from k dual vectors and L vectors to a number. So once I apply t to the first k dual vectors and the first L vectors that were plugged into t tensor S, that gives me a number. And same with S. And so the number that t tensor S gives us on so many duals and so many vectors is the product of the numbers that t gives and the product of the numbers that S gives. Yeah. Yes?
Just trying to think of a comparison to like matrix stuff like you were talking about.
Mm-hmm. This is where it gets hard to use matrices because the dimension gets pretty high. The rank gets pretty high.
Yeah, for tensors that are like matrices, so like 2 by 2 or roughly like this would be like a 2 by 2 matrix times a row vector with 2 elements times a column vector with 2 elements.
If you tensor a 2 by 2 matrix, which is a rank 2 tensor, if you want to think of it that way, with another rank 2 tensor, you get a rank 4 tensor. So a rank 3 tensor would be like represented as a cube in 3-dimensional space. So you'd have to represent it as like a 4-dimensional thing, which is why we don't do too many matrices.
I was just asking about this operation, like doing, if we have T as like a 2 by 2 matrix,
Mm-hmm.
2 tensor, and then the duals would be like row vectors that are 2 elements, and so that's how you get just the number, is you have the 2 by 2 times a row vector times a column vector.
If you have a 1, 1 tensor, then you get to plug in 1 row vector and 1 column vector. So for example, I haven't really introduced the index thing, but when we had these Lorentz transformations, we put 1 up and 1 down. This is a 1, 1 tensor. And you can think of it as a matrix. And if you plug in, so let's call this lambda. So if you plug in lambda and you give it a vector, I guess we plug in the 1 forms first. So you give it a 1 form omega and a vector v. The formula is going to end up being lambda mu prime mu omega. Well, this thing with mixed, this is like a bitensor. Let's not, because there's 2 different coordinate systems going on here. This is not a great example. But some matrix M, you could think of it as M upper nu lower mu as a 1, 1 tensor. And then you could imagine plugging in one vector and 1, 1 form. So let's write that. So nu, omega nu v mu. And this is the same thing. If you really insist on writing it as a matrix multiplication, you could write this as omega lambda v, where v is a column and omega is a row. That is a correct matrix notation. But it's just not that important because it won't generalize past the simplest tensors.
Yeah, I just wondered.
Hopefully that helps.
I mean, we could just get like multi-dimensional cubes and write numbers on them.
Mm-hmm. Sounds great. You can do it that way on your homework. Make sure to take a picture when you turn it in. Yeah.
It's going to have to be a video because it's going to change over time.
Uh-huh. Yeah, okay. Rudy, did you have something? Well, that's sort of what happened with my Lorentz transformation matrix-ish. I mean, here, no. We're just talking about there's going to be something called a manifold, which now is just R4 for special relativity in Cartesian coordinates. That's our manifold. And the tensors are defined at each point on the manifold. And the abstract space they live in at each point on the manifold is this thing here, where we introduce the, dual vector space at each point. That's what the P is here for, and the vector space at each point, and you sandwich them all together and get this is sometimes called a bundle if you mathematically inclined people, because it's locally, there's a tangent space for each point in the manifold. It locally looks like a product, but that might not be globally the case. So this is the cotangent bundle, and this is the tangent bundle. But in this class, they're just always on that structure. Yeah.
So you
tensor field, yeah.
I assume we're not going to exclusively work with tensors that are like constant on the manifold.
Oh, no, of course not.
Yeah.
In
So
fact,
really,
it's hard to even say what's meant by a tensor being constant on a manifold. We're going to have to be very precise about that. There's going to be a notion of parallel transport. But other than that,
so I guess what I'm getting at is, does like in like the box picture you drew, is there kind of like an additional input of like where you are?
yeah, all of these, yeah, these could be tensors at a point or tensor fields, but you just do this separately at every point P.
So they're like parameterized.
Yeah, you could think of them as functions of the coordinates on the manifold. Yes? Well, it depends how you define a matrix. Different people would have different definitions. So if you define a matrix as like a linear map, it's the same. You know, a 1-1 tensor can be viewed as a map from vectors to vectors, for example. So this m nu mu acting on v mu, well, there's one index left over. We could call that w nu. And so a up-down tensor is naturally the same thing as a matrix defined as a linear map from vectors to vectors. But that's only a 1-1 tensor. Now, if it's a 0-2 tensor or a 2-0 tensor, it also has n squared entries, where n is the dimension of your space. So you could write it in a table of numbers and call it a matrix, but it might not correspond with the mathematician's definition of a matrix. And any other kind of tensor besides 1-1, 0-2, or 2-0 is not at all like a matrix, because so like a tensor with 3 indices, or a tensor with 1 index, you just have, that index can take the 0, 1, 2, or 3, right? So it's just 4 numbers. So a tensor with 1 index is like a vector, right? And a tensor with, that's why I tried to give these examples here. And there'll be like 3-1 tensors that come up, the Riemann tensor, curvature tensor, and you can't think of that at all like a matrix or a vector or anything. It's just a tensor. It takes more vectors in one forms and gives you a number.
So it's like tensors are just like the generalization of like a matrix.
They're a generalization, yeah. But they also include scalars, vectors in one form. So they're the most general object that answers questions linear in small quantities in classical physics. That's why they're so useful. Okay. All right, so this tensor product construction looks sort of obscure, but once we go into index notation, you'll see it literally just means like writing the two symbols next to each other in index notation. So it'll become kind of natural. But to get to the index notation, I need to introduce a basis, right? So this defines for us tensors abstractly as maps, but just with vectors in one forms, we can resolve them as components in a basis. We can introduce a basis and ask, what is T tensor S acting on this basis element, and give that a name, a component of T tensor S. And so as I mentioned briefly last time, here's our basis. We just tensor product together the natural basis elements we already have from the tangent space V and the dual of it, V star. So maybe I better just write this again, since it came out a little unclear, and that will also give you a chance to ask questions. So the basis for, so we'll write the abstract vector tensor T. It's rank KL. So it's got slots for, K dual vectors. And what eats a dual vector? Well, a vector eats a dual vector and gives you a number, right? And so what we're going to need here for our basis is we're going to need K vectors. So mu1, and here's where I use the tensor product construction on the vectors, E hat mu K. Okay, so I've got K indices here. And then I also, run the room again, okay. I'll get much faster at using this setup as we go along. That away. This over, and I can get my tensor product written out nicely so you can all read it. So I'm tensoring all this together. So these vectors can handle eating up the k1 forms, right? A vector eats a 1 form and gives you a number. And then I need elements of my dual basis new 1 tensored in with theta hat new L. So these can eat up the L vectors that were plugged in. And then in order to make my tensor T actually act linearly, all these things by definition are going to act linearly. Now I can just take linear combinations. So I write components T. I need upstairs mu1 to mu k. And I need downstairs nu 1 to nu L. Okay. So the thing on the right are our basis elements here for KL tensors, and these are the components of the tensor, and this is the abstract tensor, right? So we've had this equation now for vectors and 1 forms, and those equations are special cases of this general thing that you pick one basis E hat mu for your tangent space for your vectors, just pick it, and then you get a basis for every tensor you could write down by this construction. And it's an exercise in writing out definitions to check that the components of the tensor product just end up being, you write them next to each other. So if we have a tensor T, so let's do an example T tensor S abstractly, or rather T tensor S. Let's do simpler examples. Let's do let's take 2 vectors and get a 0, 2 tensor. So let's imagine we had V equals V mu E hat mu, and W equals W mu E hat mu. So 2 vectors. So what is V tensor W? Well, we just tensor them, and we have this tensor product basis. So it's V mu W. I better use nu here because I already have a mu in that equation. E hat mu tensor E hat nu. And so you could then write this as, by the definition of the components, this is clearly V tensor W, the abstract things components, mu nu, and the basis E hat mu tensor E hat nu. Okay, so we can see from this equation then, this then implies that the components V tensor W, we're getting to the punchline here, mu nu, from this equation, have to be equal to this because they're hit with the same basis, and those are linearly independent. So the coordinate components of V tensor W are literally, you write V mu next to V nu, okay? And if the math of all this doesn't float your boat, just think of this as tensor product. You just literally write the components next to each other. You get an object with more indices, and that defines a tensor. Yes?
Do you mean V mu W nu?
I certainly do. That you can shout out. You don't have to wait for me to call on you. I just make those kinds of stupid mistakes all the time. I don't even notice I write the wrong thing or say the wrong thing. Yeah?
So what is that? So we get the tensor product first between the basis vectors and then V and W?
First? Yeah, I skipped a step. I could have written V mu. I could have written parentheses V mu E mu tensor W nu E nu. And then just because everything is linear, pulled out the V mu W nu.
Right.
That's what's going on.
I didn't understand. So firstly you did the cross with the tensor product between E's, and then
Yeah.
you did it with V and W.
No, the left-hand side is V and W. So all I did is I noticed that because I have an expression here that is the red thing times basis elements, By definition, that red thing is the coordinate components mu nu of the tensor V tensor W. It, you're not satisfied?
I'm saying we just given V and W, right?
Yeah.
We did the tensor product, right?
Yeah, and I computed its coordinate components.
So how did we get those two expressions? Right?
Which two? This?
Yeah, this and the right hand side.
From the definition of the tensor product. Well, from the linearity of the tensor product. I mean, the ability to pull V, I mean, right, you write V tensor W equals, we can be very explicit, V mu E hat mu tensor W nu E hat nu. Are you okay with that? Okay, so then the claim is I can pull this W out, and I can pull this V out, and I can just write V mu W nu E hat mu tensor E hat nu. And now I have this step. Okay, so maybe I shouldn't have skipped it. Okay, other questions? Yep.
In the definition of the tensor product, and we wrote T tensor product, that I think you have it up there, and it says something about the first elements. Yeah, so you take T, the first K dual, and then the rest of the dual. It seems to imply that there's ordering.
Oh, absolutely, absolutely, excellent point. So T tensor S is not equal to S tensor T, because that would correspond to swapping the ordering. Thank you for reminding me to say that. Yeah.
So the ability to pull out, there's this linearity, or is it linear independence?
Linearity. Linear independence is when I asserted that because of this equal sign here, I was able to sort of cancel the E hat mu cross E hat nu. Right? The formal way of saying that is by the definition of linear independence. I factor this out and write it as V mu W nu minus V tensor W mu nu times E hat mu E hat nu. The definition of linear independence is that that thing times it must be 0. Yeah, we really don't have to worry too much about this stuff. We can, I'm happy to go through a more mathematical version of this if people are frustrated by this cavalier presentation, but it's not a focus of the course. Yeah, well, okay.
So, to get back to the point that Edgar brought up, the T tensor S not being equal to S tensor T, that's basically because the way we notated it, we were just saying the first K whatever, first K basis elements, or
vectors you're plugging in, yeah.
If you switch the order of S and T, all you would have to do is then kind of
the last L element,
rearrange
yeah.
the order, right? And
yeah.
then they would be equal again.
Yeah, so
you just have to
well, for example,
use the
I
same-
could also do W tensor V mu nu,
Yeah.
and that would be W mu V nu, which is the same as swapping mu and nu up here, right? Because this is ordinary multiplication to compute, so it's the same as mu goes to nu. And so as we pass, we're not going to see too many tensor product symbols after today, honestly. We're just going to work entirely with component notation, and we'll just realize that when you write V mu W nu, well, that's a different thing as V nu W mu. It's just different, and so. Yep.
Just to, I guess, get back to commutation thing, would it be correct to say that, like, T tensor S of, like, V tensor W is the same as...
T tensor S of V tensor W?
Yeah, so T tensor S, like that big tensor thing of, like, V tensor W would be the same as S tensor T of W tensor V?
Yeah. As long as they're compatible, as long as your tensor can really act on the type of object W tensor V you want to put in,
Obviously,
then
if
yes.
it's like,
Yeah.
They're like 20 to 20
Okay.
tensors.
I think we should. I think we should do some index stuff. So let's discuss the things you can do with tensors to get more tensors. So one of the things we've already seen is tensor product. You can take any two tensors and just write them next to each other, and you get a new tensor which has higher rank, right? So here we tensored together two rank 1 tensors, vectors, and we got this thing with two indices. So it's a 2, 0 tensor. Oh, I should point out from this basis, probably useful to say from, what? Okay, probably useful to say from this that you can think of a tensor. So a K, you can see here that maybe that's better in another color. Keep things, so a KL tensor has K upstairs indices and L downstairs indices. And honestly, if all you remember from all this stuff is this fact, you'll be okay with tensors. It's not so bad, right? Just have to be able to manipulate them. So here's another manipulation you can do. It's called contraction. So we've already seen an example of this. So if you take sort of seen an example. If you take a tensor T mu nu, okay, what you can do is get a new tensor, the contraction of T, which has the components T mu mu. Remember, there's a sum. Okay, so if you take one up index and one down index, and you sum over them, that defines a perfectly good tensor. And it's a very useful operation. So you can do it on a tensor with more indices. You could do alpha, beta, gamma, delta, sigma, right? This is a 2, 3. Did I do something wrong? Thank you. Exactly. I told you I'd do stuff like that. Drives my wife crazy. All right. Gamma, delta, sigma, 2, 3 tensor. And we could contract on, second upstairs, and I don't know, third downstairs. This is a valid thing. You can check by writing it out in the basis and checking it's independent of basis and so on. But just trust me, we're allowed to do this. So we could write S, let's call it mu. So I'm going to change beta to mu. That was the second upstairs. Gamma, delta, and the third downstairs is also mu. And so there's again a sum. Okay, and so this thing is now, notice mu is summed over. So it only has one upstairs index and two downstairs indices. So it's a 1, 2 tensor.
Can you contract on indices that are either both upstairs or both downstairs?
No, that won't define a good tensor. And the same reason that we think of vectors acting on one forms as an okay thing to talk about, but not vectors dotted with themselves. We'll need the metric to do that. Yeah? Yes, this is a scalar. This is a 0, 0 tensor, and this is a 1, 1 tensor. Yeah. And that's called the trace of the matrix. So.
That generalizes the arbitrary dimension.
Well, dimension, you mean the dimension of the underlying manifold or the number of indices? Rank, yeah. Yes?
And we can just say we do this. Like, you can just be like, I contracted it. Like, is there
Yeah.
like a...
You can take the trace of a matrix. You can contract the indices of a 1, 1 tensor. Right, the interesting thing about trace, which you learn in linear algebra, is it's independent of the basis, right? You change the basis of the matrix, the trace is invariant. That's why it's an interesting operation. The same thing is going on here.
So is like the contraction on like that basis
basis,
vector
yes.
chosen for the ith and jth.
Yes, that is what you can go and show. And if you want to see someone write out all the annoying math stuff, you can read Wald's book. I don't think Sean bothers, which is the approach I'm taking here. But you do have to check that. There's no pretty way to define contraction abstractly in terms of linear maps. You just say, I plug in the same basis vectors for one upstairs slot and one downstairs plot. I plug in, E hat for the upstairs spot, theta hat for the downstairs spot. I sum over the 4 basis vectors that I plugged in, and I call that the contraction, and I check its independent basis.
Is this the same as multiplying by the Kronecker delta of the respective components?
Not really. Kronecker just relabels things, right?
Oh, like if you...
Mu alpha would be T.
Well, I'm saying if you were to multiply that by Kronecker nu mu.
Kronecker nu mu. Yes, that is the same. But and you can view that as also just relabeling the index. Like if you think of the Kronecker as something that sets nu equals mu, then indeed, that's one way of thinking about it.
T mu.
Do it wrong? T mu mu. Yep, thank you. Yep, okay. So contraction and tensor product are pretty much the only things you can do. In flat space, you can also take a derivative. And I'll get to that a little later. In curved space, we have to think much more carefully about the notion of a derivative. I need to tell you how these things transform. It's useful when you change bases. So it's exactly what you would have thought. Recall that a vector v mu transforms according to the notation as this, forward Lorentz transformation. A one-form omega transforms according to the notation as this, inverse Lorentz transformation, now from prime to unprime, because it's the only way the up-down rule will make sense. And you can guess the transformation law for any tensor. You just have one factor of the Lorentz transformation matrix for each one. So for example, if I wanted to change a 2, 1 tensor, I just kind of write out what I know already. I have T mu nu alpha. I just set up my 3 Lorentz transformation matrices, and I make the indices line up. So I need an upstairs, I need an upstairs mu prime to match that upstairs mu prime, and an upstairs nu prime to match that upstairs nu prime, and I need a downstairs alpha prime to match that, and then I fill in, as usual, I haven't left enough room, and then I fill in the mu I need here. Notice that I'm fastidiously not writing these indices right on top of each other. You might reasonably wonder why I'm doing that, since I've emphasized that upstairs and downstairs are really very different things. Vectors and dual vectors are really very different. Well, shortly, we are actually going to introduce a metric, and a metric is going to give us an isomorphism between upstairs and downstairs, or a map, rather, between upstairs and downstairs. And so we really do need to keep track of this one is up and in the first slot, and this one is down and in the second slot. We can't just write them on top of each other. OK, so for a general tensor, the rule is the same, right? Each index has a rule that comes from the corresponding rule for vectors in one forms. And this is called the tensor transformation law. And, it's important in physical, like in the stress tensor example where you're worried about rotations. If someone rotates the coordinate system, you have to keep track of how the force in this direction, force from this direction going in this direction changes its description when you rotate what you mean by directions. And similarly in space-time, when we're mostly worried about Lorentz boosts, you have to keep track of the same thing. OK, so I'm not going to write out the formal thing with k upstairs and L downstairs. That would just be k Lorentz transformation matrices and L inverse Lorentz transformation matrices. Now, some people actually define a tensor as a collection of numbers that transforms in this way, as opposed to a linear map from vectors to reals. It's, at some level, a matter of taste. But I find the linear map definition a little more physical, easier to think about it as answering a physics question. But you'll find some books that just say a tensor is something that transforms like a tensor, and then it's like done. Landau, yeah. Older books generally. All right. So there's a very important tensor. Let's do some examples. We've already talked about how vectors in one forms are tensors. And there's one we've been talking about a lot, or a little bit anyway, metric. So we called it eta mu nu. And we just said it's an object with two, slots, and we often wrote it as a matrix, but it's not really a matrix in the sense, because it has two lowered indices, it's really a 0-2 tensor. So it's got 0 upstairs. Oh man, struggling computer again. And so that's a very useful tensor. And what is its meaning? Well, if we act eta, so it's a 0-2 tensor, so it wants two vectors, v and w. And what number does it give us? Well, you just sandwich in v mu w nu. Not sure I said this, but this is the general rule for how a tensor acts on its component, acts on the vectors or one forms you put into it based on component notation. It just follows from that basis construction where e hat was defined such that, we derived another way of saying that is we derived this formula when it was omega, a one form acting on a vector, and this is just the same calculation. When it's a tensor acting on two vectors, you just end up summing over mu and nu. And this thing has a physical interpretation. This is the space-time interval. Or I guess it's the space-time interval when v equals w. Right, so if you imagine one vector v, the computer seems to last only about 45 minutes before it gets slow. So, if we're in space-time now, we're in space-time now, so t, x, and we just think of our good old friend, the position vector, which we're not going to have in a curved space-time, but if this thing is v, then what we've been talking about before as the space-time interval is just, so eta, the metric, acting on vv is the space-time interval. And more generally, eta acting on v and w provides a kind of inner product between v and w. And we'll think more about the interpretation of that later. But the most important thing, so we can think of this as inner product. But importantly, it's not positive definite because of that minus sign in eta mu nu. So when you do inner product in linear algebra, you often define it as a bilinear map such that it's always positive and it's only 0 when you plug the 0 vector in. It's just not true here, right? In fact, the more interesting case is when the inner product is negative. That's the time-like case that we talked about. So for a time-like vector, the inner product with itself, in this sense, is negative and tells you the time elapsed on the clock. Wolfgang?
No, I was just going to harken back to you saying not to call it a dot product because that reflects specifically on the idea of length. And since
No, this is the dot product. This you can call the dot product. What you can't call the dot product, this is very different from omega acting on v equals omega mu v mu. This is not the dot product.
So if the
this is.
So this confuses me a little bit more because I was expecting the dot product to this might be my faulty memory, but reflect on the idea of length and the idea that you're not going to.
It does if.
You're not going to have a negative length.
Suppose v, well, that gets back to the interval. So the interval is the generalization of the dot product. You don't have to call it dot product, but it's the generalization. And in particular, if I took v mu to have components 0, so it's a purely space-like vector in this frame, it's, it refers to simultaneous events, 0 times some spatial vector a in the space components. If I do that, then because eta mu nu is just ones in the space components, then, eta mu nu v nu is in fact equal to a dot a. Right? When your simultaneous events, it reduces to the dot product. It's the space-time analog of the dot product. And when it's negative, it's the square root of minus that gives you the time elapsed.
Sure, okay.
Rudy, do you have something?
I was gonna say that stopping and starting recording might fix the problem, but it looks like it's working.
Okay, I'll try that next time. Yeah.
So, what is just eta mu nu w nu? Without the v mu.
What a segue. What a segue. Am I going to do that next? That's called raising and lowering indices. It's very important. I have to get to it today, so I'll speed up if we don't.
Yeah.
But I'm not going to do it yet.
Okay.
The first thing I'm going to do is give you one more example. Yeah, Peter?
I noticed we write this as a 0-2 tensor, so that the two indices are always down.
Yeah.
Then I guess we'll get to this. But then how can you switch up with down? Because you can only sum an up with a down. So
We'll get there. We'll get there. Yeah, in 10 minutes. Okay. So we're also going to define the inverse metric. Now, we're going to use a funny notation. We're just going to use upstairs mu nu on the same symbol as the metric to denote the inverse metric. Okay, so this is defined as eta inverse. And so the equation that defines it then would be, nu rho equals delta mu rho. Okay, so this is the identity matrix, if you want to think of it that way. And this is some kind of matrix multiplication. And so our notation for inverse metric is just upstairs index. Okay, so it's a notation. Upstairs on eta means inverse. Now, for eta, it is its own inverse, right? Because this metric is, a diagonal -1, 1, 1, 1, and so is eta upstairs, right? Same thing. But in curve space, that won't be true, and we will need the difference. So remember this notation, okay? If I put the indices upstairs on the metric, that's called the inverse metric. Another example of a tensor that we will study not on this week's homework, but on next week's homework is the electromagnetic field. So the grad students who have already taken E&M2 have probably seen this. Undergrads might not have. F mu nu is a 0-2 tensor. And it's built from the electric and magnetic fields as following. So I'm going to represent it as a matrix, a table of numbers, minus E1, minus E2, minus E3, E1, 0, E3, minus B2. Thank you. 2, E3, minus B3, 0, B1, 0, minus B1, B2. Okay. You don't have to ferociously copy this down. It's in the book and so on. Why do we say this is a tensor? Why aren't we content with E and B fields? Well, when you worry about electric and magnetic fields according to different Lorentz frames, they have a very complicated transformation law. Like, it's hard to write down. It takes a few equations. But that transformation law is exactly the tensor transformation law if you define this tensor. So the electromagnetic field really is a 0-2 tensor. It really isn't a pair of vectors. Okay, that's the message. We'll get into that more deeply in future lectures in preparation for some homework problems on that. And now I can do the promised raising and lowering of indices. Yes?
I've usually seen
Okay, okay.
What is?
The rabble are clamoring for raising and lowering. I'm sorry, I hope you know I love you all. I don't mean rabble.
I guess I was just wondering if that also means the inverse.
No, it doesn't mean the inverse. The only tensor where we define the upstairs index as meaning the inverse is G mu nu. For everything else, we now introduce, with much ceremony, a map between dual vectors and one forms, or vice versa. Before, they were totally independent things. Now we're going to introduce a map.
When you said G mu nu, do you mean eta mu nu?
Yes, I certainly do. G is what we'll call it when it's curved. Thank you. Introduce a map from, let's say, duals to vectors. And so we take a vector v, we look at v mu, we contract, or we tensor product and then contract, if you like, is the way of writing it. So we write eta mu next to it, that's tensor producting. Then we contract on the upstairs index and either index. Since eta mu nu is a symmetric matrix or symmetric tensor, we can reverse mu and nu, it doesn't matter. I'll write that out explicitly. Eta nu mu. And this thing defines us our omega, absolutely not omega. The point is now we can write v with a lowered index. Okay? So once we have this metric, which gives us more structure to use, we can now introduce a canonical way to get a one form from a vector, and that's the equation. Yes?
So going back up with this in mind, how is the dot product that you showed us different from the thing that is explicitly not a dot product?
Well, now that I have a metric, I can write the dot product. I can write the dot product v mu, w nu, eta mu nu. That was what we called the dot product, where you feed the two vectors into the matrix, into the tensor, which is 0, 2, and can accept them. But you can see here, if I look, I have v mu, eta mu nu. So this is actually the same thing as v lower nu, w upper nu. So exactly, now that I have the metric, I can hide the metric in the notation and consider this the dot product between the vector v and the vector w. But I've just lowered the index on the vector to make a one form.
So I guess like before, you showed us a one form with the vector.
Yes.
And that was explicitly not a dot product.
It's not a dot product between a one form and a vector. This is a secret notation for the dot product between two vectors, where I have used a map between vectors and one forms to produce a one form using the metric, and then I contracted, which is not a dot product.
So we're saving.
It's a formulated dot product using contraction.
So are we just like saving the term dot product for products of one forms and vector where the one form originated as a vector?
That would be true, but it'd be a kind of a confusing way to say it. The dot product is just defined on two vectors. Period. And if you want to do it in a two-step way where you first lower the index to get a one form and then contract, that's fine. That's equivalent to just plugging the two vectors into the metric, which is a map from the two vectors to the numbers.
So if something starts as a one form, we can still take that final step, but it doesn't make sense to call it a dot product.
Yeah, if it starts as a one form and you just contract it with another vector, it's not a dot product. It has nothing to do with length. Yeah.
So if you do this with the one form instead like a vector, or is it?
Okay, so we can do the other thing. We can do a map from vectors to duals. Or from duals to vectors. So we could take our omega lower mu, and now for the notation to work out, this is why the raised index notation on the metric is so good. We just use the inverse metric, eta mu nu, and that gives us our omega upper nu. Second one's wrong. This is from
The one up top is wrong.
one up top is wrong. Should use a map from, this is from vector to dual. This is from dual
Yeah, so I mean, there's no.
to vector. Omega, and I can also write this as omega nu mu. So notice that the metric, I didn't say that, is a symmetric tensor. So this we call a symmetric tensor. And the electromagnetic field is an anti-symmetric tensor. So F nu mu is equal to minus F mu nu. And in general, you could be symmetric or anti-symmetric just on one pair of many indices.
What happens if the metric is not just all ones, if it has different values?
Then the inverse metric looks different, and that's what happens in general in a curved space.
Do you get any, is this raising and lowering, it still works totally fine? Like you don't have like extra constants you have to multiply?
Yeah, you can raise or lower any index on any tensor, right? In other words, this construction also defines a map between, k, L tensors and k minus 1, L plus 1 tensors. So, for example, if we had a tensor T mu nu rho, that could be related to a tensor T mu alpha rho eta alpha nu. So you see the alphas line up to sum over, and the nus are both free indices. And there'll be a homework problem this week where I just ask you to check a bunch of equations to see if they're well defined, just so you can practice letting the index notation do the math for you. And that's how the raising and lowering works, okay? And so I made a huge deal in the first few classes about how one-forms and tensors are separate things. It's not a dot product when you contract them and so on, but that's really great to keep in mind so we know what structure is being used where. But pretty much for the rest of the course, we're going to have a metric. It's going to be curved because the metric is the object that encodes the effects of gravity. And so we're going to blur the distinction. We're just going to raise and lower indices at will. Vectors and one-forms are going to be kind of the same most of the time. It's just keep in mind there's always a metric under there letting you do that. You're using the curvature of space-time when you relate a vector to a one-form. Evan?
So is there any sort of special meaning if you take two duals and raise one of their indices and then contract them together?
Like define a dot product? I don't think it's too useful, no. I think you should think of vectors as representing infinitesimal displacements. And so those are the things where you care about, like the space-time interval for those. One example, I guess, is the normal vector to a surface. If you have a surface in space, we normally think of it as a normal vector. But the natural thing is you take the gradient, right? But that's really a one form. So there's a normal one form. But sometimes it's helpful to then raise it and think of it as a vector. That's the one exception I can think of right now.
Is there a mixed metric tensor? Or
Yeah, let's figure out the mixed metric tensor. So let's take the upstairs metric tensor, and we're trying to get eta mu alpha. So how do we do that? Well, we need to lower it with the metric. So we need to sum over nu and write alpha. Anyone know what this gives us? What? Yeah, it's a Kronecker delta by definition. Because remember, this was defined as the inverse metric. And this is the matrix multiplication between the two. So by definition, this is the Kronecker delta.
And that will be...
This will be true even in curved space. Yep. Good question. This is another good one to think about in the last few minutes. Sometimes this is called trace, right? Trace of a matrix is one upstairs, one downstairs. So what's the trace of the metric? So you compute that as eta mu mu. Not you, Hongji. 4 in this class. It's the dimension of space, right? This is literally, this thing is the Kronecker delta, right? So this is literally trace of this matrix. Okay, so it's a little funny because if I say trace of eta, what's the trace of the metric? You might think, oh, that's -1, 1, 1, 1, and so it should be 2. But that was just our sort of table of numbers representation for the 0, 2 tensor eta mu nu. When you trace, you have to have 1 up and 1 down, right? And so the 1 up, 1 down object is the Kronecker. And so the trace of eta is 4, or more generally, the dimension of the space you're in.
I don't like that.
Get used to it. I mean, you can talk to me as you get used to it, but I got a few more things I need to do today to make sure we keep up. No, it's not. It's not at all similar.
I guess it would make sense to not just be 2, because you can choose the metric to be -1, 1, 1, 1, or 1, -1, -1, -1. So like then the physical properties would be weird, because you can just decide that the trace is
It's an interesting exercise to imagine how we could set things up differently and what would go wrong, but it's hard to do that in class. So the one other thing I need to tell you about is derivatives. So derivatives emphatically cannot be taken of tensors in the way you think when we're in curved space. We'll get to that. But in flat spaces, so in a flat plane or in flat space-time, as we've discussed, then taking a derivative does give you a tensor. Okay, so a partial derivative, d by dx mu, where remember, we're in a universe where these are a Lorentz frame, right? All of this only applies in Cartesian coordinates and inertial frames as we've defined. We're doing our vectors and tensors as if those are the only coordinates in the universe. But if you do that, and you take any tensor, I don't know, alpha, beta, gamma, this thing is a good tensor with 4 indices. Okay? So we usually write it as partial mu t alpha beta gamma. So that's just notation. But it's a sort of nice notation because the mu really looks like just one of the 4 indices. Okay, and so this is a good, it's now a 1, 3 tensor. Okay, and this thing here was a 1, 2 tensor. So when I say it's good, you can check that it plays nicely with all the constructions we've introduced, or you can just check that it transforms according to the tensor transformation law. Yeah?
Are we going to initially prove that d dx super mu transforms like a 0, 1 tensor, and d dx sub mu transforms like a 1, 0 tensor?
I'm not going to define a raised index d by dx. I might every once in a while write it, but it's not very helpful. Derivative is naturally a down index object. Much like the gradient I argued was a 1 form. df of a gradient of a function we said was a 1 form because you don't need the metric to answer questions with it.
So we're not going to ever differentiate with respect to vector with its index lowered?
Oh, no, you can do that. In fact, this has an index lowered. What you can't do is somehow have the index on the derivative be raised. So this d by dx mu counts as a lower index in the notation.
I guess like we're differentiating with respect to x super mu?
Yes, there is no x lower mu.
We're never going to differentiate with respect to that?
No, x is a coordinate. We're not going to raise and lower indices on a coordinate. That's hopeless in curved space-time where you lose this natural identification between the coordinates and the vectors. So raising and lowering is for vectors. Coordinates are really not vectors.
What about if you have a velocity derivative?
Have a what?
Velocity derivative. For velocity derivative.
A derivative with respect to velocity? Okay, so now you're like on phase space or something. So we're not going to study that. We're studying space. Okay. So in other words, the derivative is a map from KL tensors to K plus 1 L tensors. Okay. Whoops. K, I got backwards. KL plus 1. Okay. So it just adds one lowered index.
Does it add components to the tensor itself?
Yeah. The new tensor, you now have to plug in a vector to eat up the little down index here, right? Which is sort of which direction are you differentiating in, much like the gradient. So the gradient example, the gradient of f is now a one index object. It's got a downstairs index. It needs to eat a vector to give you a number. And the interpretation of the answer when it eats the vector is how fast did the function you take the gradient of change in that direction represented by that vector. So more generally, you can do that with any tensor with any number of up and down indices in flat spacetime in Cartesian coordinates. And we'll define a generalization for curved spacetime as well. There's probably one other tensor I should tell you about. Let's put it up with the examples, maybe. We can find some room. Okay. So it's the Levi-Civita tensor. Put it over here. So Levi CIVI, I think. Civita tensor. Yep. And so epsilon mu nu rho sigma. So now we're in 4 dimensions. We're going to need 4 of these things. And it's just defined to be totally antisymmetric. All right, so totally antisymmetric, which means swap any 2 indices. And you get a minus sign. So for example, epsilon mu rho nu sigma, I've swapped the middle 2, is equal to minus epsilon mu nu rho sigma. Similarly for all the other coordinates, and then you have to pick a normalization, and Sean uses this one. Yeah.
Is it really the case that if you swap any 2 indices, you get a minus sign? Because usually we say number 5 permutation.
You could define it that way. You could give it +1 for an even permutation, -1 for an odd permutation. But when you swap 2 indices, you swap from an even to an odd permutation.